What we're going to look at today is section 3.4 direct variation. What direct variation means, simply enough, is there a relationship between x's and y's? Are they completely equal to each other or not? What you typically see in a direct variation problem is y varies directly as x. Are they equal, or is y equal to x? Well, no. Do they have a relationship? Yeah. Somehow, there's got to be something else put into this place right here so it makes them equal. What we typically see is y equals kx. You have to multiply x by something to get to the y. There's a relationship there. We just need to make sure that it makes it equal. It's not necessarily this piece here, it's this one here. When we talk about constant variation, we've seen the word constant. We talked about the word constant when it comes to slope. What a constant variation means, or constant proportionality means, you have the same number over and over and over again. This k value right here is your constant variation, or your constant proportionality. It's also, when we start looking at slope-intercept form, it is also the slope. Why? Because what does the slope do? It rises, it runs from point to point. And then it rises the same amount, and then it runs the same amount. It rises the same amount, and it runs the same amount. It's going to get that relationship between the x's and the y's. So as we look, slope as a constant variation, look at the graph, look at the picture, think about what's happening. We're going from 0, 0, this piece right here, to 0, 1. Well, look at the graph even further. It's not labeled, but we can definitely label it. Go up 1, 2 units, and over 1 more, we hit another solid point. Go down 2 units, and over 1, we have another solid point. And do that again. What's happening? We're creating a line. This line, if my rise is 2 and my run is 1, we have a slope of 2 and a slope. Look at the equation that they're giving us as well. What do you see? Y equals 2x. This constant of variation, or this constant proportionality, is 2. They use the slope formula. We talked about that. You can look at the difference of your x's and y's. You can simply count it on the graph as well. Same concept. What's going on with this line? It's not positive this time. It is negative. Look how you get from point to point. From 0, 0, we count down 1, 2, 3, 4. So we go down 4 and over 1 for the slope this time. Can I go the other direction, pick up another point? Well, let's count. 1, 2, 3, 4, and over 1? Yes, I can. It is constant. That is our slope. What is the equation this time? Well, y equals negative 4x. Because in order for me to get to point by point, I need to multiply by negative 4 this time. Slope formula, you can see it. Okay. What if we go backwards? What if they give us the equation and they ask us to show what it looks like in graph form? Well, looking at this, same thing here. This piece right here is my slope. How do I get point by point? Well, let's just start graphing. Starting at 0, 0, we need to go, your choice, either down 3 and over 2, or up 3 and to the left 2. Your choice. Are we going to the same place? Let's find out. 1, 2, 3, and over 2. So that's down 3 and a positive 2. Or I can go up 3 and backwards 2. Is that forming a line? Sure it is. You notice where I started the graph? On these problems, our graph pieces, they start at 0, 0. Start at the origin. We'll talk later in a different section about how we know it always starts at the origin. What do you think? Did you look at this picture, thinking on your own? Slope of 2, that's our constant sitting right there. Which ones can I completely cancel out? A. Why? Okay, this is a slope that's negative. That's a negative slope. What other one can I get rid of? D. It's also a negative slope. These are both going down. So it's either got to be B or C. Now I have to figure out slope. I got to consider the rise and the run 2 to 1. If I count B, it rises 2, it runs 1. There's my answer. Compared to C, this is a rise of 1, this is a run of 2. Slope of 1/2. So that doesn't work. Summary concept, you'll find the same thing in your book. You'll see what happens every single time. When we have a positive slope, this is our function right here. We have a positive slope that's going up. This is when k's are greater than 0, positive. If our k's are less than 0, we have negative. You'll notice again, both these graphs starting at 0, 0, starting at the origin, or goes through the origin. Here's what we see as words. This is what I started the whole thing on. Suppose y varies directly as x. When y equals 9, x equals -3. Again, you're looking for the relationship. Does 9 equal -3? Well, no. There has to be something. We'll call it a k because that's what it is. What did the k have to do to make this work? Well, this is algebra. This is why we did the math. This is why we solved. How do I find this? I go through and I solve for k. I divide by -3, divide by -3. K has to be -3. What is my equation going to be? Y equals -3x. That's the relationship between the y's and the x's. Once I have that equation established, I have the y equals -3x, then I can start answering more questions. If I have y equals -3x. Now it says, use the direct variation equation to find x when y equals 15. Okay, so what do? This is my substitution. Seen it, done it. 15, -3x. Divide by -3. X has to be -5. What if they asked me the same question and said, well, what's y going to be? So here's another example. What's y going to be when x equals 2? Well, put the 2 into the equation. Y is -3 times 2. Y would be -6. So once we have that equation established in algebra, we're using the concept of substitution. You can pause this and you can look at this example, see if you can get it correct. You should get C. This is a great real-world example. This is probably one of the best ones we can look at. Is there a relationship between miles and hours? I think you know this. If you look at the relationship, we've got distance is some sort of rate times time. This same formula, distance equals rate times time, we're going to concentrate specifically on this later on. Right now we're using it in very, very simplistic terms. I think you all realize that if you drive for 55 miles for 1 hour, you travel a total of 55 miles per hour for 1 hour. You travel 55 miles. If you travel 55 miles per hour for 2 hours, I think you know that's 110 miles. The relationship is there. This right here is my rate. This right here is my time. This right here is my distance. This formula is used through multiple math classes. Well, in our example here, if I talk about distance equals rate times time, there's a direct relationship between distance and rate, or distance and time, depending on which one you call the constant of proportionality or the constant of variation. If I plug my numbers into this problem, distance in this example is 330. Time is 5.5. R, my rate, this just became the constant. this question is asking is how fast is this person driving? Because if we know how fast they're driving, if we can find out what the rate is, which is simple math, divide by 5.5, divide by 5.5, my rate is 60 miles per hour. Now I can ask you the questions. How far am I going to go if I drive for 4 hours? Well, I have an equation. Y equals 60 times t, or distance equals 60 times t. So my distance would be 60 times 4, which obviously 240 miles. Or if I'm going to go 600 miles, to make it easy, I still have my rate, which is 60. How long will it take me? Well, divide and divide. Time would be 10 hours. We know in obvious cases this is averaging because you could not go for a constant 10 hours in the car. There's going to be a need to stop and do other things. But I think it's a great example to see where constant proportionality comes in real life settings that you guys actually know and you understand. If you need more examples, please make sure you're looking on the ConnectEd website. There's other examples there. Please take a look at the homework. It's on the ConnectEd site as well.